We're going to talk about logarithmic functions. And then we'll go back and finish up the examples we didn't get on the bottom of, or back and front, whatever, of worksheet 2, okay? Worksheet 3 just talks about the definition of a logarithmic function. The big thing you need to know is that it is the inverse of an exponential function. So we'll do an example like this in a minute, but if you graph y equals 2 to the x, you would put in a 0, get out a 1, put in a 1, get out a 2, put in a negative 1. Anybody? What's 2 to the negative 1? 1/2. 2 squared would be 4. So it's going to look like this. All right. The inverse of that function is log base 2 of x, which is going to go this way, because remember the definition of an inverse is that it reflects across the line y equals x. All right, I have a video clip for you to watch quickly on logarithms, if it goes. It's just to kind of help you remember the definition that hopefully you learned last year. It's just like 3 minutes, it goes fast.
How does the difference between 0.00000000398 and 0.00000000398 cause one to have red eyes after swimming? To answer this, we first need a way of dealing with rather small numbers, or in some cases extremely large numbers. This leads us to the concept of logarithms. Well, what are logarithms? Let's take the base number b and raise it to a power p, like 2 to the third power, and have it equal a number n. We get an exponential equation, b raised to the p power equals n. In our example, that would be 2 raised to the third power equals 8. The exponent p is said to be the logarithm of the number n. Most of the time, this will be written log base b of the number equals p to the power. This is starting to sound a bit confusing with all the variables. So let's show this with an example. What is the value of log base 10 of 10,000? The same question could be asked using exponents. 10 raised to what power is 10,000? Well, 10 to the 4th is 10,000. So log base 10 of 10,000 must equal 4. This example can also be completed very simply on a scientific calculator. Log base 10 is used so frequently in the sciences that it has the honor of having its own button on most calculators. If the calculator will figure out logs for me, why study them? Just a quick reminder, the log button only computes logarithms of base 10. What if you want to go into computer science and need to understand base 2? So what is log base 2 of 64? In other words, 2 raised to what power is 64? Well, use your fingers. 2, 4, 8, 16, 32, 64. So log base 2 of 64 must equal 6. So what does this have to do with my eyes turning red in some swimming pools and not others? Well, it leads us into an interesting use of logarithms in chemistry, finding the pH of water samples. pH tells us how acidic or basic a sample is and can be calculated with the formula pH equals negative log base 10 of the hydrogen ion concentration, or H+. We can find the pH of water samples with hydrogen ion concentration of 0.00000000398 and 0.00000000398 quickly in a calculator. Punch negative log of each of those numbers. And you'll see the pHs are 7.4 and 8.4. Since the tears in our eyes have a pH of about 7.4, the H+ concentration of 0.70398 will feel nice on your eyes, but the pH of 8.4 will make you feel itchy and red. It's easy to remember logarithms. Log base b of some number n equals p by repeating the base raised to what power equals the number. The base raised to what power equals the number. The base raised to what power equals the number. So now we know logarithms are very powerful when dealing with extremely small or large numbers. Logarithms can even be used instead of eye drops after swimming.
Yeah. That music was not recorded that way. They recorded it. They played it backwards.
Did everybody get a copy of the pretest and their mastery manager sheets? All right. Everybody got a copy of the pretest? Okay. I'll give you some time at the end of class to go over it. For today, this may help you get a few right on the pretest. All right. The letters they use I find kind of helpful. The log base b of a number is the power. That's because it means b to the power of equals the number, okay? The exponent, power, is the answer to the logarithm question. When I teach this to students who are really struggling in Algebra 2 or something, I just draw little pictures and remind them that the triangle goes here, the square goes here, and the circle goes here. Okay, you're just rearranging the numbers. Everybody okay? You've got to memorize that.
Why not just write it like this?
You have to be able to go back and forth. Okay? They're going to give you this and ask you to write it this. They're going to give you this and ask you to write it like this.
There's going to be questions like, write this in logarithmic form, and I'm going to forget that.
You won't forget.
I hope not. You'll have done enough by then. Okay. All right. So the other two things it says at the top of your notes up here, guys, is that when you have log base b, that's supposed to be a b, when you have this form, these two numbers must be positive. You can't put negative numbers there, okay? The number b can also not be 1, because that would have no meaning. 1 to any power would be 1, right? All right, so Riley, I'll pick on you. Rewrite this one. No? Can someone? You can phone a friend.
Is she asking you?
Okay, Riley, do this one then.
17 to the 2 power, or whatever. You know what I mean?
Okay. We good? Everybody remembers doing that over and over last year? How about rewriting these? What? You okay? You got that? I don't know if you asked me to go back. All right, how does this one look as a log equation? Anybody?
Log base a equals
The answer to a log is the exponent power. The answer to the log. So Jared, what would this one look like? The base? Okay. This is when I tell you that the next quiz has a no calculator part, as in no calculator, none, zero, zip. Okay? You have to be able to rewrite logs. You have to be able to graph basic simple logs like power 234, base 234. You have to be able to simplify logarithms like we're going to talk about on the next few slides without a calculator. All right. These are basic properties. I'm going to quickly go through how they work or why they work. The first one says log base b of 1 is something. If we rewrote that, we'd have b to what power equals 1? Anybody? Anything to the 0 power is 1, right? So that's why this one works. The next one says log base b of b equals what? Well, if I rewrite that, I get b to some power equals b. This would just be to the 1, right? Everybody okay that that one makes sense? These next two, students just kind of memorize that they cancel each other out, but let me talk about this for a second. This says log base b of b to the x. Right now this is written as a log. Rewrite that as an exponent for me, and what would it say? B to some little box equals b to the x. So what has to go in that box? So log base b of b to the x, the log base b of b is just 1 basically, so you just get x. All right, and that leaves one more. It says b to the log base b of x. Okay, this is written as an exponent right now, so we want to rewrite it as a log. You would take log of this base b of this number equals the exponent, which is log base b of x. So once again, the box has to equal x. Everybody okay? All right, so it's just rewriting, but it's trying to teach you to memorize and save some steps. All right, the same is true of a common logarithm, which is just base 10. They don't usually write this. They just use log to mean base 10. Everybody okay with that? And those same properties all apply. Now, I don't have an answer to why this isn't NL, but it's LN for natural log. It's probably like the order you say it in French or something. Logarithm natural, I don't know. Latin something, but it's natural log. And I don't, guys, I don't know why sometimes I write it with that L and sometimes I write it with this L. That's just the way my fingers work the pen. I don't know. Natural log of 1 is E, ln of E is 1. Okay, so this is really equivalent to log base E. We just don't ever write that. Everybody okay? All right, so we just went through all those properties. The only thing you need to know is that if you try on your calculator to do a log base of anything and you put in a negative number, you'll get a note that says non-real solution. That's really helpful until you take a quiz with no calculator. Then you have to know that this is not possible, that you can't take the log of a negative number, because there's probably one on the quiz that says find the log of -6 and okay. What this is asking is 10 to what power equals -4, and you can't raise a number to a power and make it change to a negative. You could get +4. It's a logarithm. Yeah. That's how it's the log of 4. All right. So these are the kind I would put on a quiz with no calculator. This is really asking us to do what? Okay. Can you think about that? 25 is what? Yeah, it's 5 squared, and what put it down in the denominator? Yes, this is 5 to the -2, so the answer to this is -2. You can get a negative out, you just can't take the log of a negative. All right, this one is saying 3 to what power is the square root of 3? What power is the square root, guys? 1/2. Good job. Yes, the answer is 1/2. All right, C, anybody figure out those rules? What happens with ln and E? Yeah, they basically undo each other, so you just get 7. If you rewrote this, it's base E, so it would be E to what power equals E to the 7th, so it's just 7. Again, ln and E undo each other, so we just get 5. 10 to the power of and log base 10 undo each other, so we get 13. We doing okay so far? Need me to rewrite that one? This is written as an exponent. Says 10 to some power equals what? We rewrite it as a log. We'd have log base 10 of what equals the exponent. And base 10 is understood here, so this is just missing the 13. I just practice writing them back and forth so that they make sense. All right, couple more. Log base 7 of 7 means 7 to what power is 7? Okay, what happens on number 2? Yep, the base and the log exponent take care of each other. And number 3 would just be 2. What about number 4? 6 to what power is 36? All right, this one takes a little more practice. 3 to some power is 1 over 81. It's got to be a power of 3, guys. So 3 times 3 is 9, right? Another 3 would be 27. I'm thinking it's got to be 4, but 9 times 9 is 81. That's a bunch of 3s, right? So this is 3 to the 4th, but what made it go down to the bottom was, so the answer here is negative 4. Could you do that with a little practice? You got to think about it, but you got to think about rewriting them both as powers of 3. What about 6? Yep, x squared. All right, I have more practice on this, but I think we'll use it as a warm-up tomorrow, okay? We're just going to keep going today. The next thing is a quick example that uses a formula. I'm going to skip some of the examples because all of the word problems in this section just ask you to plug numbers into a formula. This one says the ln of A minus the ln of P equals RT, and it says here A is the current balance, P is the original principal, R is the rate as a decimal, and T is the time in years. How long will it take for her balance to be 6,000? We want her new value to be 6,000, given that she started with 3,000. And the rate is 6%, so what are we going to put for R? 6 over 100 or 0.06. Yep, good job. And we're trying to find T. The only thing to know is when you put this in your calculator, you do have to close the parenthesis because it brings up an open parenthesis there. And after you've typed all that left side in, you're going to need to do what? Divide by 0.06. So grab your calculator, type in ln of 6,000, close parenthesis, minus ln of 3,000, close parenthesis, enter, and then divide by 0.06 to get the T by itself. Anybody get a value for T? Nobody? Did you get 11.6? Okay. We will eventually talk about the fact that when you're doing compound interest, they only compound it as often as they tell you. If it's compounded quarterly, they only do it quarterly. So you would actually maybe need to round up to the nearest quarter of a year. Continuous interest like this, you just round to some decimal. And actually, I'm going to let you round to like the nearest tenth on all of them, okay? I'm not going to worry about whether they would really compound it that often. All right, again, this is putting numbers into a formula, so I'm going to skip it. If you want to go back and do this, you do need to put in 1 million like this in for the E, and other than that, it's just a straight up typing question. All right, what we need to talk about is graphing logarithms. I talked about this just a second ago at the beginning of the lesson. We talked about if you graphed y equals log base 2 of x, it's really just the inverse of y equals 2 to the power of x, okay? So you could find ordered pairs and then just flip them around. So that's what we're going to do, and then we're going to talk about all these properties, but I'd like to just do an example. I'm going to come back to this slide. I'm not going to spend much time on this one. It says log base 6 of x, so what I did was I found ordered pairs. 6 to the 0, 6 to the 0 is 1, 6 to the 1 is 6, 6 to the negative 1 is 1/6. Does that seem okay? And then log base 6 of x, you just flip those around to get 1, 0, 6, 1, 1, 6, negative 1, and graph it. That's what we're going to do on this question. So what are we going to start by doing? Because you will have to do one of these without a calculator. So I'm going to start by doing 3 to the x. And then I'm going to do the inverse of that. So put some numbers in. 3 to the power of. What are some points on that? 3 to the 1 is? Okay, what else do you want to put in? 2. 3 squared is? What else? 0 and negative 1 are good choices. 3 to the 0 would be 1, and 3 to the negative 1 would be 1/3, right? Okay, we don't need to graph that one. What we need to graph is log base 3 of x. Yes, 3, 1, 9, 2, 1, 0, 1/3, negative 1. Some of you are good enough at logs that you could think about putting numbers in here, but for most of us, it's easier to just generate these first and flip them around. So watch the graph paper. It's kind of funky. 3, 1 is over here. 9, 2 would be just off the edge over here by the number 10 up there. 1, 0 is here. And 1/3, negative 1 is way down here. They have it stretched kind of funny. I won't do a very good job trying to connect those, I'm sure. All right, let's fly through these questions. What is the domain? Left to right. Yep, there's an asymptote here because you can't take the log of a negative number. Does that make sense? Okay. Positive 3 to any power is never going to become negative. So when you flip it around, it's not. So it's 0 to infinity. The range, bottom to top, is all real numbers. Yep. Yep. Intercept. This had an intercept at 0, 1, but our log has 1, 0. It is an x-intercept only. Doesn't cross the y-axis ever, which makes it an asymptote. You can fill that in. There's an asymptote at the y-axis, which has an equation of what, guys? Good job. X equals 0. All right, did I skip something? No, asymptote was next. End behavior is a little weird because the end behavior, it doesn't ever actually, the left side never approaches negative infinity. So you really would write, as x approaches 0, this graph is going to get more and more negative. As x approaches infinity, y is going to approach positive infinity. Remember how we talked about this as x approaches 0 from the right? Do you remember that? We talked a little bit about that little notation. I'm not going to ask you for end behavior of this, okay? Increasing or decreasing. As I go left to right, this one is always increasing. All right, now I'm going to back up and talk about what happens when you shift these. Remember, anything in the parentheses affects horizontal, left or right. Anything on the outside of the parentheses or on the entire function affects up or down. So talk me through these real quick. What is this doing? Something for. Shifting where? Left 4. Whoa, I can't write. So here's the original one in blue, and here's the new one in red. What would this one do? 2 things. Yes, reflect over the x-axis. So now instead of going this way, it's going to flip over and go this way. And then this on the back, it's not in a parenthesis, so it's down 5 on the whole. Yeah, I don't like that they don't write that. I wish they just wrote this so you were clear that it's not in the parenthesis. But they do the same thing when we get to the trig functions. They don't always close the parenthesis here or put a parenthesis at all. And this one, guys? Left 2, okay? So the blue moved over to the left 2, and then it stretched a little bit faster going up. All right, so let's see what we need to do to ours. What do we need to do to ours according to this up here? Right 2 and reflect over x. Yep. Okay. So this point that was at 1, 0 is now going to be at 3, 0. It doesn't actually flip, right? Because it's on the axis. We okay? This point that was at 3, 2 is going to move to the right 2, which will put it at 5, 1. It was actually at 3, 1. My bad. It's at 5, 1. But then what happens? It reflects over, so it's here. This one that was at 1/3, negative 1, we have to move it to the right 2, okay, and then reflect it up here. Where's the asymptote, guys? The easiest way for me to think about this, there was an asymptote here, and when we shift it to the right 2, it's going to be, yes, here's the asymptote. And remember, it reflected over, so it's now going this way. Okay. Can I skip going through each of the different quantities here? The domain would actually be 2 to infinity. The range would be still negative infinity to infinity. The asymptote would be at x equals 2. And so on. We okay? Yeah, and I'm not going to ask that anyway. All right. This is a question that's just asking you to plug things in, read and plug the numbers in and do the formula, okay? It just wants the rate. So I'm going to skip this one. I think I'm going to be done on this. I'm going to go back and do some from yesterday. We can do a couple of those as a warm-up tomorrow if we need to. Just, this is what I want you to be working on tonight. I hope you're ready, staying on top of this assignment. This is 3.2, page 178. It says this on the assignment sheet, okay? Try doing 1 through 24 without a calculator. Now, if they ask something like this, no. That's not, I'm not going to ask you to do that without a calculator, okay? No, that's not going to be without a calculator. I don't think there's any of those thrown in there. I think I picked so that there weren't. I think you can do them all without a calculator. We can talk about questions tomorrow. Right now, I'm going to go back. There is an important question at the bottom of 3.1. Where did we leave off? Is that all the further we got was problem 1?
Yep.
Okay. I'm going to go back and talk about a few of these then. In 2007, it's estimated the United States used about 101,000 quadrillion thermal units. We're going to leave quadrillion as a unit. I'm not going to bother to write out all those zeros. If U.S. energy consumption increases at a rate of 0.5% annually, does it say continuous?
No.
No. So we're looking at using... Remember this guy?
You said we don't have to have these equations on our...
You do. We'll see. It's plus or minus depending if it's growing or decaying. This one says increases, so we're going to use plus. And we're going to use original as this amount of quadrillion of thermal units. Increases. Now be careful, this has a decimal in it, so some of you will forget to move it over, but we still have to move it twice. 0.005. And from 2007, whoops, I don't know what I was circling, 2007 to 2020, 2020 minus 2007 is 13 years, so we need to the power of 13. Quick typing.
Bless you.
I'm getting 107.
1.23 to the times 10 to the negative.
I don't think so. What did you do?
Wrong. I put times 0.005.
There we go. Okay.
I was like, well, that's a really small number.
And again, be careful. The label would be quadrillion of thermal units.
Let's see if I get the right answer.
Everybody all right?
Yeah, that's definitely not 1.23 times.
All right. I'm just going to set up a couple of these real fast. Is that okay?
Sure, why not?
A number of rabbits in a field shows an increase of 10% each month over the last year. There are 10 rabbits at this time last year, so the original amount was 10. We're growing at a rate of 10% each month. So if we want months to years, though, what power are we going to raise this to? Okay. Yes, we're changing our calendar.
Let's do it.
What month are we gonna get it?
Okay.
Don't be sheep.
We can get rid of March, because then I'll stay this age forever, okay? Because that's when my birthday is. Yeah, but you'll never get any older. All right. I'm going to set these two up quickly because they are talking about two different things here. The original population, do you have this one? Yes? Okay. It is declining. What does that mean? So we're going to do 1 minus 0.06. They want you to do it twice, 5 years and 10 years, which there's really no point. Okay. This is the one I'm concerned about. Do you remember what we do when it says continuously?
That's what is natural.
Yes, but we're going to use something close to this. Does anybody remember what it said when it said declining? What we or to make the, because there's no minus, plus or minus in here. Yes, the rate is going to be negative. Okay, so we're going to do 12,426 e to the negative 0.06 times 5 years or 10 years. I'm going to trust that you could type those in. Everybody all right? Okay, Miranda needs a special help.
I don't know what's
This
wrong
is the
with you.
question I wanted to get to. Yes, absolutely. Guys, this is the one I wanted to get to because there's one like this on the quiz. It is on the calculator part, not the no calculator part. Okay? And there's also one on the homework like this. It says, assume the population of Miami-Dade County is growing exponentially, and we have these 2 points in time with a difference of 10 years. Everybody all right with that fact? We're going to use this as our original amount, and this is our new amount because we want to know the growth rate. Yikes. Any ideas? Equal to. Yep, I'm going to use R because it's a rate. Good job. Perfect. I'm doing a great job. All right. Now we got to know how to solve that. Okay. We're going to divide first. I don't want to round yet, so I'm just going to write this, okay? I don't want to round because if I divide it out, it's going to be ugly. Then I have 1 plus R to the 10th. If it said squared, we'd square root. But it's to the 10th, so we need to do the 10th root, which is possible on our calculator. I always like to do it as a fraction. I'd rather do that than try to find that crazy 10th root thing. What is the power we need to do both sides to? Not to the 10. 1 over 10. There we go. We need to do both sides to the 1/10 because that will get rid of this and we'll have 1 plus R. So now I'm going to type this mess in. 2.25 divided by 1.94 to the 1/10 power. 1.0149 if I go a few places out. 1.0149, is that what I said? Then if we subtract 1, we get R is approximately 0.0149, or about what percent?
14.9.
No.
1.4. Oh my god. I'm done.
2 places,
I'm
about
done.
1.5% if I round.
I'm so done.
Okay. It says now write it as an exponential equation that would be our model for finding future values. So I'm just going to use y equals 1.94, 1 plus 0.015 or 0.0149 if you want, to the t, where what am I using for the original? What year? I used the 1991, so therefore t would be years since 1990. If you decided to put the 2.25 out in front, your t would just say years since 2000. All right. The trick is the second part of the question, we do not know how to do algebraically. They want to know when does it hit 2.7. Yes, we are going to graph on our calculator. We're going to put in y1, this equation with a power of x, and in y2, this equation. What is t representing, or x? Yeah, number of years. I went out to 25 years. How high do I need to go up? What is the population trying to hit? 2.7. So I just did 0 to 5, okay? I get this one starts at 1.9 and grows. This one comes at 2.7. Yeah, you could have just gone to 3 and you would have been fine. Well, it's 2.7 million, but yes. Okay, so here's the graph. I put these equations in. This one just takes a long time to open, so I usually don't use this one. But it is pretty because it's color. Here's the window I used. Here's the graph I found, and what are we interested in?
The intersection.
Okay. If you finished your pretest, you can turn it in, but feel free to just turn it in tomorrow. I'll give you the first 2 or 3 minutes to finish up what you know. It's not a grade. I just want to know, do you remember some of this or not? So this answer was 22.2, guys. So the actual answer to the question would be 1990 plus 22.2.
Can we just do the auto ask feature on our calculator to find it too, since we didn't find intercept point? Like if we just grab
I'd rather,
did auto ask and we asked for the 2.7.
but you're asking for a y value, not an x value. So you'd have to set it differently, I think. I don't know how to do that. So this would be sometime during 2012. Whoops.
For the record, 10 to the 0.60205999113 equals 4.
Okay. So you need to finish this lesson as well, this assignment on page 166 right here.
I almost